Hello and welcome. In the next few lectures, we will discuss topics from graph theory. Graph theory is one of the most popular areas in combinatorics. One of the main reasons it is so popular is that it is very easy to convey the ideas of a graph theory question and explain it to a person who is not an expert in that area. But even more importantly, it is popular because it has a wide range of applications in many areas, especially topics from computer science, biotechnology, chemistry, engineering branches, and several other topics. This is because graphs, as we'll define soon, are representing relations between pairs of objects. And it is a way to visualize the relations in a nice way, so that one can see what is happening just in a pictorial manner. This is one of the main reasons, like the area became popular, and we will see what this is about. We will look at some of the basic results and notions, and some few important theorems from graph theory. So let us start with looking at what are graphs. So for the time being, we will define what we call simple graphs, and we will just call it as a graph. So for the time being, when I say graph, what I mean is a simple graph. And what is a simple graph? A graph is a pair of sets, let's say G equal to V and E, where the elements of the set V are called vertices. So this could be a set of objects, and the set E is a set of two element subsets of V. So the elements of E are called edges. So for our purposes, a graph is this, that you have a set V whose elements we call vertices, and a set E of let's say binary relations, or a set of two element subsets of V, which we call the edges. Now, let us look at some examples. We start with the one simple example where you have four elements in the vertex set V, which we call A, B, C, and D. Now, the edge set is set of two element subsets of V, and here we define E to be set A comma C, A comma D, and B comma D. Okay. So these are the three two element subsets which form the edges of the graph. Another example I give, let us say V is Z, which is a set of all integers, and two elements A and B belong to the edges if and only if the difference is 1. Okay. Now, in this case, it happens that the vertex set is not finite. Okay. Let us look at one more example. We look at the set V as 1, 2, 3, 4, and 5. Now, in this graph, let me define edges as set I comma j when the difference between I and j is actually equal to 2. So whenever the difference between the two numbers is equal to 2, then we say that there is an edge between them. So these are examples of graphs or simple graphs. Now, a graph, a G is said to be finite if the vertex set and edge set are finite. Since we are looking at simple graphs, once the vertex set is finite, we will also have the edge set to be finite. So for our purposes, a graph is finite if the vertex set V is finite. Now the cardinality of the vertex set is called the order of the graph, which is the number of vertices in the graph. Now, what we usually use to denote the order of the graph is, G within, the graph name within two horizontal bars, and which is the called the order of the graph. Now, the size of the graph, on the other hand, is the number of edges of the graph, which is denoted by the symbol nom of G, or the size of G. It is not the norm. In this context, we will use it as size. So the size of the graph is always the number of edges, and order of the graph is its number of vertices. Now, as I mentioned, the main advantage of using graphs is the ability to visualize relations. Okay. So, as we mentioned, the edges are two element subsets, and the two elements, the subsets can be thought of as, binary relations. Like, whenever there is a relation between two objects, we can say that there is an edge between them. So this is one of the reasons, like, it is applicable in many areas. Like, for example, you want to study the transport network, right, of different cities, and you have the cities, you have the connections between the cities, different routes. Now these routes can be made as edges, right? And if there is a direct path from road from a point or city 1 to city 2, then I can say that there is a edge relation between city 1 and city 2. Right? City 1 comma city 2 is an edge. Now this can be carried to other areas, like when we are talking about people, the relations between people, or in a computer, we can talk about different components and the connections between them, or in a chip, for example, or in web, World Wide Web, or social networks, then neural networks. All these things can be represented as graphs. So this is one of the main reasons why it has a wide range of applicability, right? Electrical network. Now, so it will help if we can actually visualize these relations. So what we do to visualize is to represent it as a picture. And how do we do that? So we take your the graph, look at the set of vertices. Now the vertices we will map to distinct points on the plane. For the time being, we'll assume we'll draw it on the plane. So we will map the vertices to distinct points on the plane. Now, when two points, right, or two vertices are in an edge relation, right, when there is a relation between them, which forms an edge, then what we do is that we will draw a line segment or a curve connecting these 2 points, right, the corresponding points on the plane. Okay, so this will give you a picture, right, of the graph. So let us look at an example to see what we mean. So here I have the graph with the vertex at V equal to A, B, C, D, E, and F, and the edge set. So this is the vertex set A, B, C, D, E, and F, right? Then we have the edge set E is equal to set A, B, then set B comma C, set A comma D, set C comma E, set B comma F, and set E comma F. There is a comma missing. Okay. So we have these edges. Now what we have done here is to map these points A, B, C, D, E, and F to different points on the plane R2. Right. For example, A is mapped to some point here, B is mapped to some point here, C is mapped to another point, right? D is mapped to a point, E and F. So all these points are mapped to, all these vertices are mapped to distinct points on the plane. And now since AB is an edge, right? A comma B is an edge, I draw a line segment connecting A and B, right? This way. Similarly, since B comma C is an edge, right? I have this connection. Then I continue. I have A comma D, so I add a line joining A and D. Right. Then I have C comma E, so C and E I will connect. B and F I will connect, and similarly E and F I will connect. So then I will get a picture, right? So this is the picture that we got. Now this picture tells you many things about the relation that we may not immediately see from looking at the description, right? The set theoretic description. So if you look at this graph, for example, right, you will see there is some kind of a closed cycle here. We will define these things formally, right? A closed like walk here, right? You can find, right, B to F, F to E, E to C, and C to B, right? It's immediately clear from the picture, right? Here you need to find it out by going through each one and then see which one forms a cycle. In the picture, it is immediately clear what forms a cycle, what does not form cycle, and things like that. So this is one of the main advantages of using graphs. Right? One can visualize many relations. We will see many other examples and then how it helps. The visualization helps in the due course of our lectures. Now, we will necessarily have to define a few terms so that we will be able to look at more advanced stuff. So let us start with some definitions. So let G equal to V comma E be a graph. Okay, so we start with this assumption, and you have a vertex, let's say small letter V, in the vertex at V. Now, let me call by small letter E as the name for an edge, right? So we know that E is basically a two-element subset, right? We denote it by some name E, and that's it. Now, we say that the vertex V is incident with the edge E if V is an element of E, right? So what I mean is that so if you look at this graph, AB is an edge, right? A is a vertex which is part of the edge A comma B, right? So A comma B is an edge, and because it is a two-element set, I can talk about the vertex A being an element of the two-element set A comma B, right? So A is now an element of the edge. The vertex is an element of the edge. So if that happens, I say that the vertex V is incident with the edge E. Now, if the edge E equal to, let's say, U comma V, then we call U and V to be the endpoints of the edge E. So endpoints of E are the two vertices in that edge. Now, the names, right? Like endpoints, incidents, vertex, all these things come from the the pictorial representation. For example, if you look at the representation of the graph, you will see that the AB is a a line segment or a curve, right, in the pictorial representation, and A and B are basically the the points, right? Points A and B correspond to the vertices A and B, right? So the points are basically the endpoints of this curve, right? The curve starts at a point, let's say A, and ends at a point B, right? So this is the reason why we call these as endpoints and why it's called incidence, right? Because one can see the incidence of the point with the line segment. So these are geometric concepts. Now we say that two vertices U and V are adjacent in the graph G if U and V form an edge, right? So if there is an edge connecting U and V, then we say the vertices U and V are adjacent, or they are neighbors. I can say that U is a neighbor of V, or V is a neighbor of U, etc. So we often write, the edge U comma V, like in the graph, right? For example, U comma V is a two-element subset. Let's say that there is an edge, right? That is one of the edges of the graph. Then to save, space and writing, we often use the shortcut just UV without any space, right? So UV, if I write in the in our usual context, if I write UV, then U and V stand for vertices, and UV is an edge automatically. So unless I state otherwise, we will use this notation. And of course, sometimes we will have to change the notation depending on the type of the names that we use, or in some context we cannot use this notation. We will use the standard notation U comma V or some other notations. In that time, we will mention it explicitly. Okay, so for the time being, let us assume that when I write UV in E, that means that UV is an edge. Now, we say that two edges are adjacent, right? Two distinct edges are said to be adjacent if they have non-empty intersection. So since the edges are distinct, we say that they are adjacent if they have at least a common vertex. Now, a graph, for our purpose, since the graphs are simple, we will always have the intersection to be either, if they are not adjacent, then the intersection is empty, or otherwise it will have exactly one element. But when we talk about other type of graphs, not necessarily simple graphs, we will also come across the cases where the endpoints of the two edges could be the same. That we will not discuss in this course. Okay. Now, when you have a graph where you have a vertex set, and any two vertices are adjacent in this graph, let's say, right? So if any possible pair, every pair of vertices are adjacent, then we say the graph to be a complete graph. Okay? So if there is an n-vertex graph in which all the edges are present, right? All pairs of vertices form an edge, then we say the graph to be complete, because we cannot have any more edges, right? We need to select any two-element subset and then decide whether it to be an edge. But if we select all two-element subsets, then we cannot add anything further. So therefore, this we call as a complete graph, and we usually denote it by the letter K subscript n. Right? This is the symbol that we use. Now here are some examples of complete graphs. So you have the first one is K1, which is a one vertex graph, and there are no edges because there is only one vertex. So you have this one, right? Right, you have the one vertex complete graph. Then you have the three vertex graph, let's say K3, where you have the three possible edges, right? And yeah, here it is, right? Then you have a four vertex complete graph where you have all the four vertices, and then you have all possible six edges, right? Four choose two, right? So the two element subsets are there are four vertices, therefore four choose two edges will be there. So you have all the four choose two edges in the graph K4. You have a two element vertex set, and then you have a complete graph on two vertices, that is K2. Right, so these are examples of complete graphs. Now, again, let G equal to V comma E be a graph. We look at a subset of vertices, let's say S, and we say that this set is an independent set in the graph if between this subset of vertices there is no edge present. Okay, so for any two elements in this subset, they don't form an edge in the graph G, right? So then we say this subset is an independent set in the graph G. Now let us look at an example for independent set. So here is a graph. Okay, here is this graph. And in this graph, what I am going to do is to pick some vertices, right? A subset of vertices, let's say. So I pick, let's say, 1. Now, once I pick 1, since I want the subset to be independent, I will not be able to pick, let's say, 2 or 4, because 2 is adjacent to 1, 4 is also adjacent to 1. So if 1 is already there, I cannot pick 2 or 4 if I want the subset to be independent. But then I have the choice of either 6, 3 or 5, right? One of these 3 I can. Suppose I choose 3. Now if I choose 3, then I can say that 1, 3 is an independent set, right? Of course, 1 itself is an independent set. 1, 3 is an independent set. Now I can see, okay, can I add any more vertices to the independent? So I see that, okay, 5 is adjacent to 3. I cannot add 5, but 6 is not adjacent to 1 or 3. So I can add 6. So I selected these 3 and I got an independent set of size 3 in this graph. So I have a subset, let's 1, 3 and 6, which is a subset of the vertex set, and this is an independent set in the graph. I can talk about other independent sets, like maybe I started with 5. Now once I choose 5, I won't be able to choose 3 or 6. Now I can pick maybe 2, right, or 4 or 1. Let me say that I picked 1, right? So then 1 comma 5 is an independent set, right? Now once I picked 1, I cannot add 4 or 2, so I cannot add anymore, right? So I have a 2 element independent set, 1 comma 5. I have a 3 element independent set, 1, 3, 6. Similarly, I can find other independent sets. Now, let me define another subgraph, what we call subgraph. So let us say that we have a graph G and you have a graph H. Okay, so H is a graph on the vertex set V dash and with the edge set E dash. So V dash E dash is an edge is a graph, let's say we call this graph as H. Now we say that this graph H is a subgraph of the graph G equal to V comma E if V dash is a subset of V and E dash is a subset of E. So a graph H is a subgraph of G if V dash is a subset of V and E dash is a subset of E. Okay. So this is very important. We will come across the independent sets and subgraphs quite often. So let us look at some example. So here is an example. Let us say G is the graph V comma E, where V is the set 1, 2, 3, 4, and E is the set 1, 3, 2, 4, and 3, 4. Now I have H is the graph V dash E dash, where V dash is the set 1, 3, 4, and E dash is the set 1, 3, and 3, 4. Now H is a subgraph of G because we can see that 1, 3, 4 is a V dash, which is 1, 3, 4, is a subset of 1, 2, 3, 4, and E dash is a subset of E, which is 1, 3, 2, 4, and 3, 4, right? So E dash is 1, 3, and 3, 4. So therefore, the graph H on 1, 3, 4 and with that set 1, 3, and 3, 4 is a subgraph of the graph G. Now, in this, I can look at another subgraph. For example, our independent set, right, was a subgraph, right? There is no edge, but it is a subgraph. The edge set is the empty set, right, which is a subset of the edge set anyway. Now, if you look at this graph, you can clearly see many of its subgraph, right, immediately, right? For example, I can just look at the, the graph formed by 1, 2, and 3, right, which is a subgraph, of course, right? So the vertex set is a subset, edge set is a subset, and therefore I see a subgraph clearly, right? Similarly, I can say that, okay, I can add more, right? I can add maybe, right, 1, 2, 3, and 6. So I have a subgraph on 1, 2, 3, and 6. Similarly, I can see other subgraphs, right? For example, I may choose 4, then I select 5, then I select 6, I select 1, then I choose the edges 5 and 6 only. So now in this case, for example, we have 1, 4, 5, 6, the vertices as a subset, and then the edge 5, 6 is a subset. So therefore, it's a subgraph of the graph. Now let us look at another example. I have the graph G equal to VE, where V is the set A, B, C, D, E, F, and E is the set A, B, A, C, A, E, D, E, C, E, and E, F. Okay. So I have this graph G. Then I have the graph H. Let's say, right, with the vertex set V dash, which is A, C, E, F, and E dash, A, B, D, E, and D, F. Now, clearly, you can see that V dash is a subset of V because A, C, E, F is a subset of A, B, C, D, E, F. And E dash is a subset of E, which is A, B, D, E, and E, F is a subset of A, B, A, C, A, E, D, E, C, E, and E, F. Now, A, B, D, E, and E, F, right? So therefore, I see that V dash is a subset of V and E dash is a subset of V. But now, I claim that H is not a subgraph of G. Now, why is this? If you have been careful, you should have already noticed it. It is because our definition of the subgraph says that H is a subgraph of G, right? What was our definition? Let us see. Right? A graph H equal to V dash E dash is a subgraph of G if V dash subset of V and E dash subset of V. Now, what is the definition of a graph? We said that a graph is having a set V as the set of vertices and a set E which are two element subsets of the set V, right? Then we say it's a graph. Now, what we have here, for example, in this example, is V dash is a ACEF, right? And E dash is AB, DE, and EF. But D is not a vertex of V dash, right? So since D is not a vertex of V dash, DE cannot be an edge in the graph with the vertex at V dash. So therefore, H equal to V dash E dash is not a graph. So since H is not a graph, it is not a subgraph because our definition says that H is a graph first and then only it can be a subgraph. So it is not just sufficient to have a subset of vertices and subset of edges, but we should also make sure that the edges are using only the vertices of the subgraph that we are looking at. Okay. Now, a subgraph of subgraph, let's say H of a graph G is said to be an induced subgraph if for every, let's say, pair of vertices X and Y in H, the edge XY belongs to the graph H if and only if the edge XY is an edge in the graph G. So whenever the edge is present in the graph G, I will add it to the graph X. Of course, only between the vertices of X, right? So the vertex set is a proper, not necessarily proper. It could be any subset of the vertex set. Then, but the edges for an induced subgraph, we cannot choose the edges. The edges come automatically from the graph G. All the edges which are present in between these vertices will automatically come here. Okay. To see an example, let us look at the graph G here, right? With vertex at 1, 2, 3, 4, 5, and 6. And I select a subgraph, with the vertex set, let's say 1, 2, 4, and 6. So I select 1, 2, 4, and 6. 1, 2, 4, and 6. Now, since I am looking at induced subgraph, right? So looking at induced subgraph, the edges will come directly from G itself, right? So since I look at this vertices, I let's say mark 1 here as vertex 1, and then I take 2. Then I have 4 and 6. But now I notice that there is no edge connecting 1 to any other vertices 2, 4, or 6. So therefore, that edges are obviously not there. Then 2, 4, there is an edge. So I select 2, 4. 4, 6, there is an edge. Therefore, I also choose 4, 6. Right? Those edges will come. I cannot say that, okay, I don't want the edge 2, 4. Because if I don't choose edge 2, 4, then what I get is not an induced subgraph. It is just a subgraph. It is a subgraph, but it is not an induced subgraph. So this one is a subgraph of the graph G, right? But it is not an induced subgraph. On the other hand, if I add all the edges that are present in G between these vertices, then it is an induced graph. And I can denote this fact that I am looking at induced graph by writing the graph within square bracket the subset of vertices that we are looking at, because that is clearly now defined, right? What are the edges? So therefore, I can just write the vertex set and say that, okay, this is the subgraph, induced subgraph that I am looking at. So here are some more examples, right? So you have the graph G. The graph H and H dash are subgraphs of the graph G, right? H is a subgraph because we can see clearly that the vertex set is a subset. If I want, I can also name it, right? So 1, 5, right? Now, with this, one can see that, of course, H is a subgraph of the graph G. H dash is also a subgraph of the graph G. On the other hand, H is an induced subgraph because if I select all the vertices 1, 2, 3, and 4, all the edges between those vertices in the graph G are present in H. On the other hand, H dash is not an induced subgraph because H dash has all the 5 vertices, but then it should have all the edges between them also, right? For example, 3, 5 is an edge in the graph, but 3 and 5 are vertices here, but 3, 5 is not an edge. So therefore, H dash is not an induced subgraph, right? So this is what one should be clear of. Okay, we will continue with the topics in the next class.